Learning an expert skill space for replanning dynamic quadruped locomotion over obstacles. Our work is motivated by the strong potential for adaptive behavior by modern robotic systems that have many degrees of freedom and the power to execute dynamic trajectories. While many methods focus upon robustly tracking a single, narrowly defined behavior, adaptiveness would instead involve the deliberate use of broader regions of the robot's action space for accommodating a larger variety of tasks and challenges. Adaptive behaviors may then need to have a temporally extended scope in order to express foresight about the scenario at hand. The capability to continually replan such motions online without stopping would enable robots to handle diverse environmental challenges with grace and efficiency. This paper targets a data-driven approach to enabling this replanning capability for a mid-sized quadruped robot, Animal. In service of this ultimate goal, we leverage offline experiences to enable high-quality initial guesses to be quickly computed for tasks seen online. This type of approach, which we will refer to as data-driven trajectory initialization, or DDTI, is in essence behavior cloning of temporally extended actions. DDTI has become increasingly popular over the past decade, but substantial complications exist for applying it to sustained and adaptive quadruped locomotion. We use a software library called Tower that was designed to handle the contact changes inherent to leg locomotion and modify its formulation to be suited for receding horizon use while still preserving the freedom to adjust the timings of footfalls. Furthermore, we employ a regression model that can accommodate a diverse range of quadruped behaviors without imposing discrete categorizations and without invalidly interpolating between distinct solutions to similar tasks. The locomotion solutions produced by Tower include spline descriptions of the 6 degree of freedom base motion, as well as the swing trajectories, contact force profiles, and timing sequences of each of the 4 feet. Our expert dataset consists of many such solutions that cross linear obstacles without stepping on them. Breadth of experience is ensured by randomizing the obstacle configurations, by adding smooth noise to the naive initialization, and by using a long horizon that gives the optimizer substantial freedom. This also ensures that the dataset is not dominated by starting and stopping behaviors. We cut segments of these trajectories that are short enough to be tractable for DDTI, but long enough to permit a meaningful degree of online refinement. The task associated with each segment includes its dynamic initial state, a goal designated as perception horizon, and information about the intervening environment. This produces the dataset of task and segment pairs appropriate for use in a receding horizon fashion. At the core of our approach is the fitting of a deep neural network regression model to the dataset of segmented trajectories and tasks. To cope with the multimodality of the expert data, we elect to use unsupervised learning of a continuously valued mode of behavior. We employ a conditional variational autoencoder where the trajectory segment is the variable to be reconstructed and the task is the condition variable. This disentangles the variation of the expert's stylistic choices into the latent mode variable so that they may be accounted for independently of the task itself. For a brief illustration, consider these colorations of a 3D mode distribution, the aggregate posterior of the CVAE. When avoiding stepping on an obstacle, the expert might select a foothold on either the near or far side, but not directly on top. Thus, it is useful to spend the expressive capacity of the mode space on the length of each stride, but not on other choices that can be unambiguously decided based upon the task alone. Additionally, the rightmost plot shows that similar tasks may sometimes be paired with distinct modes. When deploying the trajectory regressor, its modal inputs are selected from the offline experience set based upon task similarity. To produce rollouts, we interleave the use of LMTR with the computation of a new task based upon nominal advancement under the previous plan. The quality of the rollout is then assessed both visually and numerically. Rollouts produced by LMTR effectively translate the finite-length expert experiences into adaptive locomotion plans of arbitrary length. The adaptive qualities are apparent in the selection of footholds, which are biased away from obstacles, as well as in the shaping of the base velocity and the adjustment of gate timings. Aggregate results, detailed in our paper, demonstrate LMTR's favorable performance relative to baseline methods. Thank you for your attention and your interest in our work. Feel free to contact me with any questions or comments, and please keep an eye out for our next work targeting control-integrated deployment of our replanning technique.